All right, so welcome back here. Today we'll be doing part two of our of my transport first homework here. And so let's begin by reading the question here. So, assuming that the decrease in air temperature with altitude can be modeled entirely by the adiabatic reversible expansion of pockets of air, ideal gas, starting from the basic equation of fluid statics, derive expressions for the first one, air pressure, and then expression for two, the air temperature as a function of altitude. And so there's a lot there, and a lot of assumptions are made to make this derivation a lot easier. So first, what I'd like to do is sort of model, what's going on here. So we have a pocket of air, and as it goes up in altitude here, it's going to expand. And I said earlier that it's a adiabatic reversible expansion. So first of all, adiabatic means that there is no heat going into the system. The reversible portion means that the P external is equal to the pressure, well, the pressure external is equal to the pressure inside. And that's about it. And so we should also realize that during this expansion here, um, work is being done to its surroundings. So we should expect a decrease in temperature. Anyway, continuing on here, starting from the basic equation of fluid statics. All right, so what is that basic equation? Well, it's the change in pressure with respect to the change in altitude, dz, is equal to rho a. So the density times the acceleration. So in our case, since we're simulating something going into the air, right, going up, our acceleration will be the will be gravity, right? So that's will be um, negative, right? Since we'll just have g be the value. So that'll be rho g. And so it was stated earlier in the question that it's an ideal gas. And so that will help us lead to an equation in which pressure is related to altitude. So our goal right now is to get an equation in which we can sort of separate it. We can identify that it's a separable differential equation, right? So then we can integrate and get our function, or I guess expression in this case. And so how does this relate to anything at all, to pressure, I guess, right now? Well, that would be through the ideal gas law. And so how does density relate to the ideal gas law? Well, density here is equal to the mass times the molar weight, right? And so this mass over molar weight is N within the gas law. So if we were to say the ideal gas law, let's just write it out in terms of this, right? That's what we would get. Rearranging it for mass, since that's what I want to sub in. Oh, my bad. This is supposed to be volume. I got it. I got ahead of myself. Density is mass per volume, right? And then relating mass to the ideal gas law. This is the equation in terms of mass, right? N is substituted by the mass divided by the molar weight. And so then solving for mass, we would get PVM over RT is equal to mass. And then we can sub it back in here. I won't draw that arrow because I'll be using that. But now subbing it back in, we get density is equal to pressure or volume, molar weight, RTV. The volumes cancel. And this is what we are ultimately left with, negative. When subbing this back into our basic equation of fluid statics. All right, sorry for the little error there. I was getting ahead of myself. So going from there, um, there's a sort of clue that we can't just continue on from here. And it's the fact that it's an adiabatic reversible expansion, right? Like I said earlier, temperature will be decreasing as it expands because work is being done by the system, right, onto its surroundings. And so temperature is also changing with altitude. And so before we can even move on to our separable differential equation, we sort of need to find the relationship between temperature and pressure, right? How does T vary with P? And well, the only relationship that sort of relates the two is the first law of thermodynamics. And well, what is that first law? It's the internal energy is equal to the small amount of heat, which I'll denote as D, is gonna be, and then the work. And like I said earlier, it's work done by the system, so it'll be minus P dV, specific volume here, pressure. And this is the external pressure, of course. And so with the assumptions that we had made earlier here, based on our model, hopefully this can be seen on my phone cam, we can sort of make some substitutions here. And so this internal energy, since it's based on since it's an ideal gas, it'll be varying with temperature. So it'll be the heat capacity constant at constant volume times dt. It's going to be equal to, since this is adiabatic, this term is 0. And since it's reversible, the P external is actually the pressure inside. And we've sort of made some progress here, right? And so this still isn't quite temperature and pressure yet. This is sort of the change in temperature with the change in volume. And so what can we do? Well, this is an ideal gas, right? And so we can try subbing in P to make it in terms of V to see if that brings us anywhere further, right? And so let's do that. And so this will be CV dt is equal to negative. So P will be looking up here. N will be 1, right? So this specific volume, right? So it will be RT over P. I mean, RT over V. RT over V dV. And now we can see that we have a separable differential equation. We just have to move the variables around. So then we get CV dt over t is equal to negative R dV over V. All right. And so, like I said, separable differential equation. Um, this will be from some initial value, right? So these will all become dummy variables of integration. Some initial value, t1, v1, to whatever value we want, tv. All right, integrate, and we get cv. Any variable to the negative one, its integration is the natural log, right? And then since we're doing it a subtraction, natural log minus the natural log is the division of those two within the natural log. And so I'll be sort of doing that substitution all in one step. So it'll be t over t1, natural log, very important. Natural log is equal to negative r, same thing, natural log of v over v1. All right, so we're starting to get somewhere here. So let's do some simplifications on this expression. So we get cv over r's natural log of t over t1 is equal to the negative of a natural log is the reciprocal of whatever's inside. The natural log of the reciprocal of whatever's inside. So we can apply that, and we get v1 over v. And so then get rid of the natural log by taking the exponential of both sides. So this front term becomes the exponent. This was 1, so this becomes just v1 over v. So we get T over T1, CV over R is equal to V1 over V. All right. And so right now we have it temperature in terms of volume, but we needed pressure. Remember, that's what our basic equation was set up for, and that's what we need to sub in for temperature to get a separable equation available for us. And so how else do we get to pressure with this volume? We did it. We just do the same exact way that we did for pressure here, using the ideal gas law to sort of convert it into the other values. And so this term here, using the ideal gas law to get the pressure in, will be V is equal to RT over P. So let me write that out. T1 CV over R is equal to, so this will be RT1 over P1, right? And then this will be RT over P. Simplify that. The R's cancel. The multiply by the reciprocal. CV over R is equal to, so you get T1 multiply the reciprocal, so the T's on the bottom, times P over P1, right? Times the reciprocal, so P's on top. And you'll notice here that we have sort of a similar term on this side. And well, we'd want to, divide it over, which is by multiplying the reciprocal. And the reciprocal is this value here. So when you multiply the two, you're just adding 1 to the exponent, right? So I'll do that. So we would get, let me move my paper up here. So that's still in view, hopefully. I can't tell. CV over R plus 1 is equal to the pressure over the initial pressure. And so where do we go from here, right? It seems like we kind of have it. We kind of don't at the same time because this exponential is kind of hard to move around. And well, if we look a little bit further in, we'll notice that there is a relationship that can be substituted into this exponent. So the heat capacity at constant pressure is equal to here the heat capacity at constant volume plus R. That is a relationship. Usually there's an N in there, but remember N is 1 for this case because we're using specific volume. And so we can sort of sub this in because this is technically CV plus R over R, right? Common denominator, CV plus R. So you get CP. And so let's sub that in. So you get CP over R is equal to P over P1. And now we can sort of solve for temperature, right? And so multiply each side by the reciprocal exponent. And that will get that out of the way. Is equal to pressure over P1. Gosh, okay. RCP, then multiply T over T initial, right? Temperature initial. And this is what we get as our equation. How does temperature relate with pressure? And so now, after all that work, we can finally sub it back into our basic equation of fluid statics all the way up here, which is, I'll box it, to hopefully get it in terms of pressure, and then we can integrate our separable differential equation. And so let me rewrite all this on the back here. So I have room dp dz is equal to negative pm g rt, and our equation that we just derived in terms of temperature in terms of pressure is equal to T1 pressure over pressure initial to the RCP. All right, so let's sub it in. So we get dp dz is equal to negative pmg. So I'm going to actually do this in baby steps to sort of make sure I don't get this wrong. T1, that is to the P1 RCP. Watch me still get it wrong. Okay. I will apply the exponent to both things in the fraction. So you get RT1 PR to the CP, or P1 R to the CP. Sorry if it looks like it's right there. It is to the exponent. Multiply by the reciprocal to get it out of the denominator. So that cancels, and then this will just be flat out multiplying throughout, right? And so this step always makes me worry that I did something wrong. I'm sure I didn't. All right, so, well, I guess this is an arrow. I can draw an equal sign here. All right, so then we get negative P M G P1 R to the CP over RT1 over P to the RCP. Common base, right? So then you can combine the two. This is technically to the 1, so 1 minus R to the CP. So you get negative P1 minus R CP. MG P initial to the RCP and R temperature initial. All right, and so now we can uh, isolate the variables and get our separable equation set up, differential equation set up. So let's see here. What do I want to do? So dpd's, oh gosh. Okay, so I'm gonna multiply dz over. So dp is equal to negative p1 minus r over cp mg p1 r over cp over rt1 over dz. Now we want to bring the pressure over. So when you're dividing that, you're negating this, all right? So bringing this over negates the exponential. And so we get p to the RCP minus 1 dp is equal to negative mg r temperature initial p r over cp dz. Initial. All right. And so we can do our separable. These are all constants, right? Hopefully I didn't do anything wrong so far. I don't think I have. So moving on. Bounds, well, these are all going to be dummy variables of integration. It's going to be that z initial, pressure initial, to whatever altitude, whatever pressure. So subbing that in, this minus 1, plus 1, right? So then divide that by the exponent. So you get Cp, oh god, over R pressure from pressure initial to whatever pressure. I'll just mark that there. Is equal to negative mg RT1 P1 R over Cp. This is 1, so it would be Z minus Z1. All right, and so I'll do this next, Cp over R, pressure minus pressure 1. This is to the RCP. Jeez. RCP is equal to stuff above, because I didn't do anything on this side. All right, bringing the R over and the CP. We get P to the RCP minus P1 to the RCP is equal to, so the R's cancel, right? So we get negative mg over Cp T1, P1, R over Cp, Z minus Z1. Add this over, so we get P to the RCP is equal to negative mg Cp T1, P1 to the RCP times Z minus Z1 plus pressure initial to the RCP. Take a common factor of that pressure initial to the RCP out. So we get P R to the CP is equal to pressure initial to the RCP times negative mg. Where's my eraser? There it is. So this will be 1. That would still be a negative number. So 1 minus mg cpt1 all right, and now multiply by the reciprocal of the exponential, and we get pressure is equal to P1 1 minus mg heat capacity at constant pressure temperature initial times Z minus Z1 all to the Cp over R. And that is how that is the air pressure expression as a function of altitude. And so how do we get to the air temperature as a function of altitude? Simple. We literally take this equation here that we just solved for pressure and we plug it in to our earlier equation all the way up here, which we solve for temperature and pressure, how they relate, and we'll get the temperature as a function of altitude here. So I'll just do the work up here because it's not that many steps. So hopefully you can see it. So you get temperature is equal to the initial temperature, big parentheses here. So you get P1, what is it here? 1 minus mg cpt1 z minus z1 all over to the cp over r, and that is all over p1. And this is all to the rcp. All right, p1's, oh, I just used up all my space. Well, anyway, p1's cancel, so we're just left with this in the parentheses to the CPR, and then all of that is the RCP. So these cancel, so you get T is equal to the temperature initial times 1 minus molar mass, molar weight, times the gravity, acceleration of gravity, heat capacity at constant pressure, temperature initial times the change in altitude. Whoopsie. There we go. And then that is the expression for temperature as a function of altitude. And that's down here was the expression for the pressure as a function of altitude. And there you have it. Thank you.